Hello everybody, this is the third video and the last one for chapter 7 of the statistical learning course. So in the second lecture, we've introduced the support vector classifier where we took the original maximal margin classifier, but we've added the possibility to have some violations of the margin. So to have points inside the margin or even on the wrong side of the hyperplane. And the idea was to have more support vectors or more of such points which would impact the optimal solution and therefore to add some robustness for our classification method. Moreover, these violations would allow finding solutions even in cases where the data sets are not linearly separable, which means that there would exist no separating hyperplane where all points on one class are on one side and all points for the other class are on the other side. So this flexibility allows to find solution when the data set is not linearly separable or and the solutions even if there's a even if the data set is linearly separable, this approach gives more robust solutions. But now the for some data sets, support vector classifier might perform very poorly. Okay, so let's take the example of this data set from the textbook. Well, here there's no linear or hyperplane that would perform well. Okay, so if you have a hyperplane like this, well, you have half of the blue points misclassified, and if you have a hyperplane like this, well, you get something like this, but this is very poor because on both sides there's a lot of points misclassified. Okay, so a lot of blue points fall on both sides, a lot of pink points fall on both sides. So here, this wouldn't be support vector classifier wouldn't be a very good approach for this data set. So in this video, we will see how to generalize support vector classifiers into support vector machines, which would allow doing a good job for these type of data sets. Okay, so and the idea, so let's go back here. The idea here is linear decision boundaries wouldn't do well. So we will see that we can still apply the support vector classifier machinery to obtain non-linear decision boundaries. Okay, so this generalization we're going to introduce is called support vector machines, which is a generalization of support vector classifier so as to produce non-linear decision boundaries. And the idea here is that instead of applying the support vector classifier on the original data set, we could apply a transformation of this data set and um, perform the classification not on the original data set, but rather on the transform predictors. Okay, so this is analogous to what we did in, for example, regression models, where instead of only taking the original data, we can consider polynomials of the original data, so like squares, cubes, etc., so as to obtain new predictors, and this would turn, for example, a linear regression into a polynomial regression, allowing for nonlinear predictions. Well, the same kind of idea can happen here. So instead of applying the linear decision on the original data, we can apply a linear boundary on the transform data, which would be equivalent to a nonlinear boundary on the original data. Okay, so same idea that we applied for linear regression, we can apply here for support vectors, support vector classifier, or in fact, support vector machines. Okay, so here we're going to use a bit of results from the optimization of support vectors, but we're not going to show this. Okay, so this is going to be a bit magic. We need, if we wanted to fully understand this, then we need to derive the solution of the support vector classifier optimization problem. Unfortunately, we won't have time to do this, so it's kind of results you need to accept without proof at this point. But for those who are interested, I encourage you to have a look at the references to understand this a bit better. Okay, so it can be shown that for the support vector classifier, the optimal hyperplane, okay, driving beta hat 0 and beta hat j from j goes from 1 to p, driving the prediction function f. So recall that when we have a new observation, we classify it by plugging the predictors into f here, which is the linear combination of each individual predictors of that observation. And if that quantity is greater than 0, we classify as 1. If this quantity is smaller than 0, we classify it as minus 1. But it can be shown that this the support vector or the optimal hyperplane or the prediction function stemming from that optimal hyperplane can also be written as this form. So it can be shown that this prediction function f can also be written as beta 0 hat plus the sum across all observations of alpha I times the scalar product between that new observation and training observation I, where the constants alpha 1 until alpha n, they depend on the training data. Okay, so it can be shown that the classification of a data point, a new data point, it depends, it's a linear combination of the scalar products between this observation and all other data points. Okay, so here the first question is how to obtain these alpha i's here. How do these relate to the betas? Well, we'll discuss that briefly now. The first thing we have to notice is that the solution or the optimal hyperplane only depends on support vectors. Okay, so for data points xi which are not support vectors, they shouldn't impact the classification of new observations, which means that if we go back one slide here, if xi is not a support vector, it should not impact the classification, which means that alpha I must be equal to 0 in that case. Okay, so that the xi, which is not a support vector, doesn't appear here. Okay, so the alpha i's are only non-zero values for i's observations I which are support vectors. Okay, so this means the classifier is said to be sparse because it only depends on a few data points, and most of the data points have zero impact. So the alpha i's are basically 0 for the vast majority of i's, which are in fact the non-support vector observations. Sorry. So taking this, here we have a summation over all observations because alpha I is 0 for all non-support vectors, we have that this classification function can be expressed as a sum. Instead of summing over all observations, we can simply sum across all elements in S, where S is the set of support vectors. Okay, and then for support vectors, how to get these alpha i's? Well, it can be shown. So again, as we said, we won't demonstrate how to do that or the dynamics of that. It's kind of a result you have to accept at this point. But the alpha i's, they can be shown to depend only on the dot products between the training observations, or scalar products between the training observations. Okay, so what this means here is that the classification function f, so all these alpha i's, they only depend on dot products between the observations. So this classification function, if we want to calculate it, we don't need to know exactly all the data points. We only need to know their dot products between each other and between the new observation x and the support vectors. Okay, so it means to perform classifications, what we need is only dot products. We don't need to know exactly the observations themselves. Okay, so to calculate the support vector classification for some observations, only dot products or scalar products are required, not knowing the observations in the training set themselves. And this is a bit surprising because you would expect that you have to know the training observations if you want to do the classification, but no, the information summarized by the dot product is sufficient. Okay, and the idea here is the dot products, they act as a measure of similarity between observations. Okay, so two observations, they're deemed similar if they have a large dot product, and they're considered dissimilar if they have a low dot product or even a negative dot product. So a negative dot product means that the vector would point in different directions, which means that the observations are very dissimilar. Okay, so the idea behind support machine is that we could use exactly the same formula than for the support vector classification, but instead of using dot products as a measure of similarity, we could use other metrics as a measure of similarity, and these other metrics are referred to as kernels. So instead of using a scalar product between two observations to determine how similar they are, we could use kernels or more general functions instead to determine their similarity. Okay, so here we can use the notation k to denote a kernel, and k xi prime would denote the application of the kernel k to data points xi and xi prime, which would represent the similarity between xi and xi prime based on this kernel. Okay, so the scalar product or dot product corresponds to the linear case where the similarity between two data points is simply their scalar product, or the sum of products of each element of each vector. Okay, so instead, what we can do here is if we replace the scalar products in the classification problem by the kernel, we'd obtain a classification function f of this form. So f is beta 0 hat plus a linear combination of cross support vectors of constants alpha I and times kernels here. So instead of having dot products between x and xi, we can use kernels here, and the constant alpha 1 until alpha n are obtained by substituting the dot products in the previous calculations by kernels instead. So you use exactly the same formula for computing the alphas in terms of dot products, but instead of having dot products operators everywhere in the formula, you'd replace them by kernels. So basically this entails exactly using all the same machinery than support vectors, but using a different metric for similarity of points, which is a kernel, and which can be different from the dot product. Okay, so examples of kernels that can be used in practice are, for example, the polynomial kernel of order d. So here, the polynomial kernel of order d is 1 plus the scalar product between xi and xi prime to the power d. So if we have d is equal to 1, then this is simply the scalar product plus a constant 1. Okay, so we can see the parallel here. So we can see that this generalizes the scalar product. And here, another example here of similarity between or kernel, which could determine the similarity between two data points, is the radial kernel, which is basically the exponential of minus alpha times, so this is the squared Euclidean distance between point xi and xi prime. So here, if you use a radial kernel, rather than two points being deemed similar if they point in the same direction, as per the scalar products indicate, two data points would be deemed similar if they have very close values in terms of Euclidean distance. Okay, so it's changing the scalar product with a radial kernel, it means that similarity uh, is uh, represented or characterized by closeness in terms of Euclidean distance instead of pointing by direction. So this is a bit analogous to the discussion we had in the clustering chapter, where we said that to represent similarity, you can use either correlation or Euclidean distance. And by changing your metric, you might have drastically different result. Well, the same thing happens here. So if you replace the dot product, uh, which kind of acts as correlation for similarity, by a radial kernel, which is meant to represent Euclidean distance, then you'll have different results. Okay, so this using the radial kernel produces what we call local behavior, and therefore observations are classified together if they're close together instead of if they're on the same side of a given hyperplane. Okay, so this induces a completely different behavior for your classification. Okay, so here we we kind of just give the end result here. So this figure, once again, it's the textbook, but this is the data we presented originally, where we said that having a single linear decision boundary would do very poorly. Well, if we apply support vector machines with a polynomial kernel, so here this is the polynomial kernel of order or degree 3, and on the right side, this is the radial kernel that we've introduced. We can see that the decision boundaries we obtain are really different. Okay, so here, instead of having a single decision, like single plane, we have two lines here which represent the decision boundary. So if you're in this tunnel here, you would be classified as red, and if you lie outside here, you would be classified as blue. And here, the dotted lines, they represent the margin. Okay, so if you're within the dotted lines here or within dotted lines here, then you would violate the margin. But if you're outside, so if you're here, you don't violate the margin. If you're in here and you're blue, you don't violate the margin. Whereas if you're here, then you don't violate the margin for red points. Conversely, for the radial kernel, we see here the local behavior where points are classified in the same class if they're pretty similar together. So if they're similar to the red points, then they would be classified as red. And if you're similar to the blue points, then you would be classified as blue here. So we can see we really have a, a clear nonlinear decision boundary, which clearly works better for this data set. And the dotted lines here, they would represent the margins. Okay, so the margins are a bit weird here. So if you're inside this little circle or oval here, you don't violate margin. If you are here, it means you're within the margin, and etc. Okay, so here for these blue spots inside these weird shape, you're not violating the margin, but if you're anywhere here in this area, you are violating the blue margin. Okay, so in a nutshell, we won't spend too much time about explaining properties of the various kernels. Okay, we're going to leave that out of scope. But what I want you to know here is that we can still use the maximum support vector classifier calculations and methodology. But when we switch the scalar product to represent similarity by some other metrics represented by different kernels, we can obtain much more flexible decision boundaries, which could work for many more data sets. Okay. So okay, what's happening here? So we mentioned support vector machines being kind of support vector classifiers applied on transformations of the original data set. Okay, and what happens with the two kernels we presented? It can be shown that the polynomial kernel or the radial kernel are indeed the support vector classifier applied on a transformation. Okay, so it can be shown that for these two kernels, there exists a function m which takes the original p-dimensional input and maps them into q-dimensional outputs, and then the results of the support vector machine classification you've seen is basically simply applying the support vector classifier on uh, these new data points in q dimension. Okay, so basically it can be shown that the kernel between any point xi and xi prime is the scalar product not between the original data points but between the transformed data point where the transformation is provided by M. Okay, so as we said, the applying the support vector machine methodology with these non scalar product kernels is strictly equivalent to apply the support vector classification on these transformed data set where M is used for transformation. Okay, so but then uh, so you'd say, well, why do we use a kernel? Why don't we simply transform the data point X and then compute the support vector classifier on these new data point? Computationally, that might seem more simple. Well, the idea here is that computing these transformation M might be very cumbersome. Okay, so for example, in the radial kernel, it can be shown that Q is equal to infinity. So the space in which we project or we transform the original data point uh, is infinite, has an infinite number of dimensions. Okay, so if we wanted to calculate these new transformed data points, we need an infinite number of predictors, which of course cannot be done for computation. Okay, so simply applying the transformation and then applying support vector classifier might not be feasible because you need an infinite number of predictors in that new space. But if we only apply the kernel, then in theory it would give exactly the same thing, but in practice it would be much more computationally convenient because you don't need to do that mapping into an infinite dimensional space. Okay, and in practice, for some kernels, we don't even know what that transformation M is. Sometimes we won't present the results here, but there are sufficient conditions on some kernels to say, okay, for this kernel, there exists some transformation M such that the kernel between xi and xi prime is the scalar product between the transformed data point where the transformation M is applied. Okay, so there are results which say there exists a transformation M such that the kernel is the scalar product between these transformed data points, but we don't even know what that transformation is. Okay, so this applying kernels allows us to even avoid having to know what is the suitable transformation to apply to data points. We can simply specify directly the kernel instead of specifying that transformation M. Okay, technical conditions on for this result, which guarantee that a kernel is is produced by a suitable transformation M. This is out of scope, but these results exist. So if you want to dig further into that question, feel free to have a look at references. Okay, so this justifies support vector machines, which are generalization of support vector classifiers producing nonlinear boundaries, and they're equivalent to applying support vector classifier on transformations of the original data set. But the good news is we don't even need to compute the transformation of the data points because sometimes that transformation it's very complicated or we don't even know what it is. We simply need to replace scalar products by kernels in the formulas, and this automatically gives us the solution we could theoretically get by transformation of the data points, but which computationally might not be feasible if we had to apply the transformation explicitly. Okay, so now one last topic, which is what happens if we don't have a binary classification problem? What happens when we have multiple classes? Because the theory outlined up to now was for binary classifications where you have class 1 and 1 or minus 1, and depending on which side of the hyperplane you fall, then you can get that classification. Okay, so now let's suppose you have more than two classes. Capital K, which is the number of classes, is greater than 2. Okay, so for this method, the textbook proposes two approaches when you have more than two classes. There's a one versus one classification approach or a one versus all classification approach. So let's start with the one versus one classification approach. So let's say you have K classes, then the one versus one, or also called all pairs approach, constructs choose two from K support vector machines, each which compares a pair of classes. Okay, so the idea, if you have classes 1, 2, and 3, so what you could do here, as a first step, you could simply drop all class 3 observations from your data set and find a support vector classifier or support vector machine which classifies between 1 and 2. Second step, you would have another support vector machine classifying between 1 and 3. So you drop all class 2 observations from your data set, and then you only keep observations from class 1 and class 3 and get a new separating hyperplane or support vector machine classifier. And finally, last step, you drop all observations from class 1 and compare class 2 and class 3. Okay, so let's try this. Let's say you have class 1, 2, and 3. Then you would do get 3 classifier, 1 vs 2. You'd get 1 vs 3 as the second hyperplane, and 2 vs 3 as a third hyperplane. Okay, so same thing. If you had 4 classes, it would be 1 vs 2, 1 vs 3, 1 vs 4, 2 vs 3, 2 vs 4, and 3 vs 4. Okay, so for all pairs of classes, you can get a hyperplane separating the various classes. Okay, and then what happens so this you do that on the training set, and then for the test set, okay, or for new observations, you would consider each of the classifiers you've had initially, and then you count the number of times each observation is assigned to each of the K classes. Okay, so let's give an example. Let's say we have a new observation, and then in 1 vs 2, let's say it's classified as class 1. Whoops, here this should be a 3. In 1 vs 3, let's say it's classified as class 3. And then in 2 vs 3, let's say it's classified as class 3. Okay, so in that case, what the ultimate result would be that the observation, you count the number of times the classifiers classify as each class, and the class which has the more count is deemed the most likely class. Okay, so here it's been classified twice as class 3 by these two last classifier. So the ultimate classification is class 3 because class 3 had 2 votes, class 1 had only 1 vote, and class 2 had 0 vote here. Okay, so basically you look at a point for all support vector machine classifiers between each pairs of points, and the class which is you obtain the more often is the final classification. Okay, so this is the one versus one approach because you run support vector classification always for one class versus another, one class versus another, one class versus another for all combinations, and these are the ones used for classification. Okay, so this is the one versus one approach. Now there's the other approach, which is the one versus all classification. Okay, so here, um, instead of, so in the previous choice, let's say you had k class. In the one versus one, you had choose two between k classifiers. Here for the one versus all, you're gonna have instead k classifiers, where on each of the k iterations you will fit all observations from class I. Okay, let's say you're in iteration small k, goes from 1 to capital K. Then for iteration small k, what you're going to do, you're going to uh, cluster or regroup all observations from class non-small k, and then you're going to do a classifier versus class small k versus all other classes. Okay, so for example, if you have classes 1, 2, and 3, then the first classification would be 1 versus the rest, and the rest is 2 and 3. 2 versus the rest, 1 and 3, or 3 versus the rest versus 1 and 2. So you can see here, if k is equal to 3, you have exactly k is equal to 3 classifier. And here, every time you make a classifier, then for iteration small k, okay, you get a separating hyperplane, or a vector of betas denoting the hyperplane, or it might be the vector machine if you apply a kernel instead, support vector machine. So here, the class small k is coded as class +1 in the support vector machine methodology, and all other classes are coded as class -1. And then what happens, whoops, among all classifiers, if you have a new observation, x0, then you can compute that linear combination, beta 0 plus beta 1 x1 until beta pxp. But here, for all of the classifications, so for iteration 1, 2, and 3, you have different value for this expression. And recall that this expression, we say it's very large when you're far away on the right side of the hyperplane, or this expression would be small if you're on the right side but close to the hyperplane, or negative if you're only on the wrong side of the hyperplane. Okay, so the classification does the best whenever this quantity here is very large. So the idea here is, for a given observation x0, we would compute this quantity for all small k. So for all the 3 hyperplanes we had in the previous iterations, and we were going to take small k, being the small k maximizing this quantity, so being the hyperplane for which the observation was the further away from this hyperplane. And this is basically entailing that we're gonna use we're gonna predict as the class for which we would have the higher confidence of being right for that classification. Okay, so here basically we test each like class small k versus all the rest, and then for a new given observation we would pick the k, or the class for which we would get the highest confidence of being right for the classification. Okay, so this gives two approach to generalize the binary classification of support vector machines to multi-class classification. So we can either use the one versus one approach, or the one versus all approach. Okay, two possible choices. In practice, what works best, you probably need to try it out and look at the results out of sample to determine what seems better. One final remark here or topic. So we mentioned earlier that there was a relationship between logistic regression and support vector classifiers. Okay, so unfortunately we won't have time to discuss that here, but this feature is discussed in chapter 9.5 of the ISL textbook. So if you want to get a better grasp about relationships between or connections between logistic regression and support vector machine, feel free to have a look at this section. So this completes the last lecture for the chapter 10 material. I hope you've enjoyed and thanks for watching.